Greetings, iCampSA students, and once again welcome to another video. Today we are gonna be doing functions. We are still doing functions, but the area of focus is now exponential functions, since we have already covered most of the functions. So the area of focus for today will be exponential functions. Okay, so when it comes to exponential functions, as the name suggests, the variable now is on the exponents. So they are a function of this nature. Y is equal to, let's say, 2. Y is equal to 2 to the power of x, for example, and then we have the variable here at the exponent. So hence why we call them the exponential functions. Okay, now let's go ahead and look at some characteristics of the exponential functions. Okay, so we have two main types of exponential functions, and here are the equations for those functions. So it's mother functions or mother graphs, the equation for the mother graphs. So this is the most basic of the exponential functions that you will find out there. The first one is y is equal to 2 to the power of x, and then the second one is y is equal to 1 over 2 to the power of x. 1 over 2 to the power of x. So you will see once we start sketching these functions that they actually come out a bit different. They come out different actually, but they are both exponential functions. Just that one is an increasing exponential function and the other one is a decreasing exponential function. Okay, so maybe so that you can get a visual understanding of how these functions comes out, let's go ahead and sketch the functions. Let's go ahead and sketch the functions. If you remember, when we introduced the hyperbolic functions, the hyperbolic function has two sets of asymptotes, the horizontal and the vertical asymptotes. What you'll see happening with the exponential functions is that they also have an asymptote, but it's just gonna be one horizontal asymptote. It doesn't have two, it doesn't have two asymptotes. Okay, so let's go ahead and start sketching these two basic exponential function. Y is equal to 2 to the power of x. We will start with that one. We can select just random values, of x in order to be able to find the corresponding y values. Okay, then for x, we will go with -1, 0, and 1, and then let's find the corresponding y values for those. 2 to the exponent -1, it should be 1 over 2, and then 2 to the exponent 0, that should be 1, and 2 to the exponent 2, that should be 2. In fact, we can increase the scale of this just a little bit, Let's add the numbers. We would add -2 and 2, -2 and 2. Okay, so 2 to the power of -2, that should be 1 over 4, and then 2 to the exponent 2, it will be 2. So another characteristic of an exponential function, the way it grows or the way it decays, it starts to start going slower and slower, and then all of a sudden it grows really quick. It grows really fast, so the trident becomes really sharp. It becomes really sharp. So as especially for this function that we are dealing with here of y is equal to 2 to the power of x, as the value of x increases, you will see that the value of y also increases, but it increases very, very, very quickly. It increases very quickly. Okay, now that we have those, we have your what you call this thing, your y-intercept at 1, because where x is equal to 0, that will be your y-intercept. Let's see if we are able to find an x-intercept. We let y equal to 0. Let y equal to 0. Therefore, we're going to have 0. Therefore, we're going to have 0 is equal to 2 to the power of x. And as you can see that this is undefined, is undefined because there are no values of x that will actually satisfy this equation, because even 2 to the power of 0 is equal to 1, so it's not equal to 2. It's not equal to 2, so we don't have there is no x-intercept. There is no x-intercept. There is no x-intercept, here. Okay, so the graph will not touch or cut the x-axis, so what you see happening here, since the graph doesn't touch the x-axis, it is essentially the x-axis acts as an asymptote. Remember I said that for these exponential functions we gonna have one asymptote, which is a horizontal asymptote, and that horizontal asymptote will find it where y is equal to 0. So I can just say, therefore y is equal to 0 is the horizontal asymptote. It's that value that the graph will approach but never touch. Okay, yeah, once we have done that, we can in fact now just sketch our function. Let's sketch our function. We're gonna have 1, 2, and 3. 1, 2, and 3. -3, -2. This is 1, 1, 2, and 3. Then we're gonna have, let me see, x values as 1, 2, 4. 1, 2, 3, 4. 1, 2, 3, 4. So it's -4, -3, -3, -2, -1. We're gonna have 1, 2, 3, 4. Let's plot the points. We have the y-intercept there at 0 and 1 here, and then we have -1.5, so it's about halfway there. 0.5, and then we have -2.25, so a half of a half will be there, and then we have 1 and 2, 1 and 2, and then we have 2 and 4. Okay, once we have this, we can now join our points. And that is how our exponential function will come out. Okay, then next, let's sketch the other function. Let's sketch the other one. Let me add a page, custom, create. Okay, so the second matter graph or basic function is y is equal to 1/2 to the power of x. So we have y is equal to 1/2 to the power of x. Y is equal to 1/2 to the power of x. Okay, so let's select some x values that we're gonna use to sketch this function. Those are gonna be, let's go with 2, -2, -1, 0, 1, and 2. Then let's find the corresponding y values. the corresponding y values. Okay, so 1/2 to the power of negative 2. I think it's gonna be 2, but let's quickly double check. 1/2 to the power of negative 2. Oh, it's 4. Yeah, it's 4. And then we have 1/2 to the power of negative 1, which is 2. And then we have 0. 1/2 to the power of 0, that should be 1. And then we have 1, that should be 1/2. We have 2, that should be 1/4. 1/4. And then once again, y is equal to 0. Where y is equal to 0, that is your is horizontal asymptote. That is your horizontal asymptote, because when we let y equal to 0, there are no values of x that we can substitute in order for this equation, which will be 1/2. There are no values of x that will actually satisfy this equation, so it's non-existent, so y is equal to 0 becomes your horizontal asymptote. Okay, now let's go ahead and sketch this function and see how it comes out. It's another variant or variation of the exponential functions, the basic exponential functions. Okay, 2, 3, 4. 1, 2, 3, 4. -4, -3, -2, -1, 1, -2, -3, -4. 1, 2, 3, 4. 1, 2, 3, 4. What is the y-intercept? The y-intercept is 1. So they have the same y-intercepts as the exponential function of y is equal to 2 to the power of x. Okay, and then where x is equal to -2, y is equal to 4. And where x is equal to -1, y is equal to 2. And then where x, 0 and 1, and 1.5, it's halfway there. And then for 2 is a quarter, a half of a half. And then once you have those, what you do next is to join your points. And that is how the other exponential mother graph of the exponential functions look like. It is how it looks like. So this one, as you can see, it's a decreasing function. As the values of x increases, the function becomes smaller and smaller, or the values of y become smaller and smaller. Therefore our function is decreasing. Okay, the function is decreasing. So that is actually the two mother graphs, of exponential functions. Anything else that we gonna do would be just the variations of these two basic graphs, or of these two basic mother graphs. So next we're gonna be looking at the general equation for exponential functions. And remember that when we are dealing with general equations, that is when we have done some transformations to the function. Okay, now let's go ahead and look at the general equation of the function. So once again, we have two general equations. of exponential functions. First one being y is equal to a multiplied by b to the power of x plus q, x plus q. So the way you can look at this one is like, oh yeah, no, it's not actually 2, it's not actually, I was focusing on the restrictions there, on the values of b, on the values of b. So yeah, that is just the general equation of the exponential functions, but we have two restrictions, and those restrictions is that b has to be can either be greater than 0 or less than 1, or b can be greater than 1, or b can be greater than 1. And the reason for that is that if b were to become 0, for instance, if b were to become 0, let's go to our function, or to the equation y is equal to a times b. Let's say b was now 0, so exponent x plus q, so you'll end up this, all of this would just cancel out. That will be equal to 0. You'll end up with y is equal to q, which is essentially a equation of a line. It's just a horizontal line. It's just a horizontal line. And once again, if okay, let me write it like this. If b becomes 0, we get that, and then let's assess what happens if b becomes 1. If b were to be equal to 1, what you'll see happening here is that y is equal to a to the power of a times b, and b, we say it's 1 to the power of x plus q. So what you see happening here is that if b is actually equal to 1, it doesn't matter to what value the x is gonna be, or the exponent is gonna be. We're always gonna get the same thing, which is y is equal to a times 1. These parts of the function will always be equal to 1, no matter what number we raise the 1 to. We can raise 1 to the exponent 1000, it will be equal to 1. So at that point, this is no longer a function, but just a equation of a straight line, and then you get y is equal to a plus q. So from this you can see that therefore I'm writing going up now. Therefore b cannot be equal to 0, and b cannot be equal to 1 in order for us to have exponential functions. Okay, yeah, hopefully that gave you guys some clarification as to why we have those two restrictions that we have there, of b being greater than 0 or less than 0. So here b is simply a fraction, because it's between 0 and 1, and here b is actually greater than 1, so it can be any number that is greater than 1. Okay, now let's quickly assess what happens when we change the value of b. So b, the value of b determines the shape and the stiffness of the graph. It determines the shape and the stiffness of the function. It determines the shape and the stiffness of the function. The value of b determines the shape and the stiffness of the function. So for the first function where b is greater than 1, this is actually the function that we first plotted of when we are coming back to these matter graphs of y is equal to 2 to the power of x. Y is equal to 2 to the power of x. That is when b is actually greater than 1. Okay, so what you see happening here is that as the value of b increases, let's say now we have y is equal to 4 to the power of x, as the value of b increases, the graph will actually get much more steeper. The graph will actually get steeper and steeper. So let's say we had this graph, that sketch as I've drawn here, that sketch I've drawn here, so we can say this one that we see there was actually maybe y is equal to 2 to the power of x. Once you have y is equal to say 3 to the power of x, you can see the function becoming something like this. It actually gets steeper, it actually gets steeper. And another important thing to note is that for this restriction where b is greater than 1, the function moves upwards from the right to the left. As you can see here, the function moves upwards as the values of x increases. As we are moving from the left to the right, the function increases like that, so that is when b is greater than 1, or that is when we have that restriction whereby b is actually greater than 1. Okay, now let's look at the second restriction. This is when we're actually dealing with fractions, fractions, and this is the one that relates to the second matter graph of y is equal to, say, maybe 1 over 2 to the power of x. So what happens with this restriction is that as the graph moves downwards, as the graph moves from left to right, the graph is actually decreasing, or it is moving downwards. It's getting smaller and smaller, it's getting smaller and smaller, or slower and slower, and what you will see happening is that by reducing or decreasing the values of b, let's say we move from 1 over 2 to 1 over 4, the graph will actually get steeper, you'll have a function of this nature, a little bit more steeper, and then as we decrease the value of b again, the function will be steeper like that again, so that's what happens when we are now decreasing the value of b, so it's the opposite for this restriction. For the first one, when b is greater than 1, as the value of b increases, the larger the value of b, the steeper the graph. Here on this second restriction, whereby we are dealing with exponential functions with the value of b that is between 0 and 1, as the value of b gets smaller and smaller, the function actually gets steeper and steeper. That's what you'll see happening. Okay, and then next we have that variable which is a. The value of a determines the vertical stretch of the matter graph. So we like to believe that if you have watched the other videos we have posted, that you are already familiar with a. So a determines the vertical stretch of the matter graph. So when we're talking about the vertical stretch of the matter graph, is we're talking about how far is the graph located from the x-axis. Not referring to the asymptote, by the way, but just how far is the graph actually stretched away from the x-axis, or in other words, a determines the vertical stretch of the matter graph, and of course, as you might be aware right now, that a negative sign will cause a reflection in the x-axis. That still holds true even for the exponential function. And then lastly we have q. If you've been with us for some time, you already know that q there is actually our horizontal asymptote. It's actually our horizontal asymptote, and it also determines the vertical shift of the graph, the vertical shift. Be careful with that. We said a, it determines the vertical stretch, and q is the shift, of the graph up and down. So we are dealing with the shift, and in other words, the value of q also indicates the horizontal asymptote. So basically the equation of the horizontal asymptote will be y is equal to q. That will be your equation of the asymptote. Equation of the asymptote. Okay, now let's go ahead and sketch these graphs now, so that we can actually see what we have introduced thus far. Okay, so here we have example number 1. For example number 1, we're asked to sketch the following functions on the same set of x's. Okay, so the easiest way to actually sketch this function is by just finding the y-intercept and just maybe one other point that lies on the graph, okay, and actually sketch the graph. So here you are already seeing that, okay, we are dealing with functions with the value of b which is greater than 1. That should already tell you that this function will be of this nature. They will be increasing as we are moving from left to right. Once you see that we are dealing with a fraction, you must know that the function will be decreasing as we are moving from left to right. So we have already identified that. What we need to find now is what is your y-intercept. So for function number a, the y-intercept, and for the y-intercept we equate x is equal to 0. Right? Therefore we're gonna have y is equal to 2 to the power of 0. This will be equal to 1. Okay, this will be equal to 1, and then we can just simply find another point that lies on the graph, and then we can sketch the graph with those just 2 points, because we can see here that we don't have asymptotes, we don't have the values of q. So if you don't have the values of q, by default the asymptote will be the x-axis, y is equal to 0. That is your asymptote. Okay, let's just find another point. Let's find y at x is equal to 0. Let me see something, because now I'm also thinking about just using a few points, instead of just one. Yeah, let's take -1. This is equal to -1, 0 and 1, and let's find the corresponding y values. Where x is equal to -1, we're gonna have 1 over 2, and 0 we already have. That's your y-intercept. 1 is gonna be 2, and then let's go ahead and do for b. So for b, the y-intercept, where x is equal to 0, we're gonna have y is equal to 3 to the power of 0 is equal to 1 again. So by now you should be able to see that all of this graph will have the same x-intercepts. Also for c, the y-intercept, where x is equal to 0, y is equal to 4 to the power of 0 is equal to 1. So they all share the same y-intercept. Okay, now let's quickly find a few points for graph number b. We're gonna pick -1, 0 and 1. Y, okay, 3 to the exponent -1. It's gonna be 1 over 3, and then 3 is 1, and it's 3, and then let's come here for the final one. Let's pick 3 values, -1, 0 and 1, and then for y is equal to 1 over 4, 1 and 4. What are we expecting here? What are we expecting to see? As you can see that, okay, from a to b to c, the value of b, it's increasing and increasing and increasing. We start with b, that is 2, and then for the second function the p is actually 3, you know, and I'm referring to this p here, to this p, this variable here. I'm referring to this variable here, that p there. And what did we say about p when we are dealing with the functions, the exponential functions of p greater than 1, is that as the value of p increases, the graph becomes steeper and steeper. So that is what we are essentially expecting to see here. We're expecting to see function number c being the steepest amongst these three functions, okay, but let's sketch and see. What happens, you know, what happens, you know, because remember that the value of p affects the shape and the steepness of the function. Is the shape and the steepness of the function. Two. Okay, so we're gonna have 1, 2, -1, -2, -1, -2, -3, -4. We have 1, 2, 3, 4. Okay, now let's sketch these functions. We'll start with function number a. We have 0 and 1 points there, that's your y-intercepts, and then we have half. Where x is -1, we're gonna have half, you know, and then we have where x is equal to 1, we have 2, so it's gonna be there. Then let's go ahead and sketch this function. I'll just sketch it in green. Yeah, just like that. Then let's go ahead and sketch the following function. We have what? We have x, where x is equal to -1. X is equal to -1, y is 1/3, which is less than 1/2, which is will be below this because it's like 0.3. And then we have the 0 and 1 there, and we have 1 and 3, that point there. Already you should be seeing something. You see that as we have increased the value of p, you know, the function has become a little bit steeper. Let's go ahead and plot the third one. The third one, we have a quarter will be there because I think it's 0.25, and then we have 0 and 1 here, where x is equal to 4, x is equal to 1, y is equal to 4. Okay, so this function are not supposed to touch the thing. The x-axis, by the way, is the asymptote. So they approach it, but they never touch it, you know. So you see that the function is now steeper. Let me quickly label these functions that we have here. We have function number a, which is y is equal to 2 to the power of x. Y is equal to 2 to the power of x, and then we have y is equal to 3 to the power of x, and then we have y is equal to 4 to the power of x. So you see that the function that has the biggest value of p, you know, of p, variable p, which is the, what you call this thing, yeah, just that p, you know, it is the most steepest of the three, you know, that function. It's actually function number c. It is much more steeper than than the other three functions, so once again we can see that as the value of p increases, the function becomes steeper. The larger the value of p, the steeper the graph gets. So hopefully this has been able to actually prove that point to you. Next, let's do this example. Okay, now we are dealing with the functions of with the restriction of 0, p, and 1. The one we're doing here is the one for I can just say p greater than 1. So remember what happens when we are dealing with this restriction, whereby we are focusing on the values of p that are between 0 and 1, is that as the value of p gets smaller and smaller, as the value of p gets smaller and smaller, the function becomes steeper. And also keep in mind that 1 over 2 is greater than 1 over 3, which is greater than 1 over 4. So which one is the smallest? The smallest is the function number c, which is y is equal to 1 over 4, has the smallest value of p. So we expect the last one to be the steepest function, because it has the smallest value of p. Okay, but let's go ahead and sketch this function so that you can actually visually see what we are talking about. Remember, changing the value of p, it affects the shape and the steepness of the function. That is what we are doing in these examples that we are dealing with so far. So we have for a we have, let's find the y-intercept. So a is y is equal to 1 over 2. In fact, since y-intercepts is actually where x is equal to 0, we can just select x values of x, -1, 0, and 1. We know that here at 0, that would be a y-intercept, so I think that really makes lives easier. So we have -1, 0, and 1. We have y, let's see, 1 over 2 to the power of -1, 1 over 2 to the power of -1. I'm not sure, I think it's gonna be 2 or something. Yeah, it's 2, and then 1 over 2 to the power of 0 is 1, and then we're gonna have 1 over 2. Okay, then let's find select three values. Let's select 1, -1, 0, the y-intercepts, and 1, and then let's find the corresponding values for the second p function. Now the p function, so 1 over 3 to the power of -1, that should be 3, I believe. Yeah, it's 3, and then we're gonna have 1 and 1 over 3. Okay, and then lastly, function number c, x values -1, 0, 1, and then the corresponding y values will be 4, 1, and 1 over 4, Okay, now let's sketch the functions. Okay, let's sketch the functions. 1, 2, 1, 2, 3, 4, 1, 2, 3, -1, -2, -3, -1, -2, 1, 2, 1, 2, 3, 4. Okay, so let's start with the first function number a, which is 1 over 2 to the power of x, where x is equal to -1, y is 2, so it's gonna be there. And then where x is equal to 0, y is 1. Where x is equal to 1, y is half. And that is your function right there. Yeah, it will look like that. And then next, let's sketch function number b, where x is equal to -1, y is 3, and then where x is 0, y is 1. Where x is 1, y is 1 over 3 below this one. And therefore after let's sketch and you have it. That is the second function. You can already see that the function that we've just sketched of y is equal to 1 over 3 to the power of x is actually much more steeper than the first function. Let's sketch the last one. Function of y is equal to 1 over 4 to the power of x, where x is -1, y is 4, and then where x is 0, y is 1, and then we have a quarter below that. Let's join our points. And to shift it a bit upwards. Yeah, I think that's a little bit better. Even that's the last function, and it's even much more steeper than the other two functions. So as you can see, what we have been said here is that for the functions or the exponential functions with the restriction of b being greater than 0 but less than 1, the smaller the values of p, the steeper the graph gets. The smaller the values of p, the steeper the graph gets. Smaller the values of p, the steeper the graph gets. Okay, hopefully this example has been able to demonstrate that for you. Next, let's get to example number 3. Okay, sketch the following functions on the same set of axes. Okay, so here we have the variable a which stretches the function away from, let's see, what does the variable a do? The value of a determines the vertical stretch. It determines the vertical stretch of the matter graph. As you can see here, that we have this matter graph, and then the variable a has been introduced here, 2 and 3, and then of course for the matter graph the variable of a is 1. Okay, so yeah, let's go ahead and sketch these functions. Let's go ahead and sketch these functions and see what we come up with. Yeah, so we'll sketch the functions on number 1 on the same set of axes, and the functions on number 2 on the same sets of axes. Not that we're gonna sketch everything all at the same sets of axes, it's gonna be a bit untidy. So for functions number 1, I think let me label them. This will be your a, and this will be your b, and this will be your c. Yeah, let's start by sketching those. So for function number a, x values, let's go with -1, 0, and 1. Let's find corresponding y values. let's find corresponding y values where x is equal to -1, y is equal to 1/2, and then 0 is 1 and 2. Okay, that's your mother graph. That's your mother graph. And then for p, function number p, x values, let's go with -1, 0 and 1. Corresponding y values where x is -1, we gonna have 1 and 2 and 4. 1, 2 and 4. Yeah. And then for c, you can punch these in your calculator in order to verify them. It's just that I can't write everything down, it will take up a lot of space. Okay, but you simply substitute these x values that we have picked of -1, 0 and 3 wherever you see x, and then the calculator should do the rest of the work. Okay, so where x is equal to -1 for the third function, we're gonna have let me see, 3/2. We're gonna have 3/2, and then we're gonna have let me see, 3, it's gonna be 2 to the power of 0 is 1 times 3 is 3, and then 2 to the power of 1 is 2 times 3 is 6. That's 6. Okay, yeah, there we have the 3 points. Now let's sketch these functions. And remember what we said about the value of a is that as it increases, the function becomes it gets stretched further and further away from the x-axis. Okay, so for function, let me start by calibrating these. We have 1, 2, 1, 2, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay, -1, -2, -2, -3, -4. 1, 2, 3, 4, 5, 6. 1, 2. Let's start by sketching the first function of a, where x is -1, y is where x is -1. Okay, let me see if I'm still doing everything correct. Okay, so where x is -1. Oh, now I'm looking at these functions, and I almost thought that we're sketching for them, but we're still in number 1. I was a bit confused by that. That's okay. Yeah, now it makes sense. Okay, so where x is -1, y is half, so it's here, and then 0 and 1, and 1 and 2. 1 and 2. So we have a function of this nature. And then function number b, where x is -1, y is 1 here, and then 0 and 2, 1 and 4. 1 and 4. 1 and 4. And then lastly, function number c. Hopefully you are already seeing that this one would be 1.5. -1 and 3/2. 3/2 is 1.5, and 0 and 3. 1 and 6. Hopefully you are seeing that as the value of a increases, the functions move further and further away from the x-axis, so the function gets stretched further away from the x-axis. This one is for y is equal to 3 multiplied by 2 to the power of x, and then the y function is y is equal to 2 times 2 to the power of x, and then lastly is y is equal to 2 to the power of x. Y is equal to 2 to the power of x. Okay, so that is what happens to the function when the value of a is being changed. The value of a, let's go ahead and remind ourselves, the value of a determines the vertical stretch of the matter graph. It determines the vertical stretch of the matter graph, as you are witnessing here. Okay, and then let's go ahead and do number 2. Number 2, we also have to sketch them on the same set of let me see. I want to see something that if we were to sketch these functions on this same set of axes, okay, but maybe it would just become too ugly. Instead, let me copy, let me add a page, custom, add a page. Okay, so we are at number 2 now. Number 2, still doing examples regarding the vertical stretch of the matter graph. Y is equal to 1/2. I'm quickly rewriting what we had there. And then y is equal to 2 multiplied by 1/2 to the power of x, and then lastly we have y is equal to 3 multiplied by 2 to the power of x. Okay, let's quickly find I'll just say this one is a, b, and this one is our c, and this one is our c. Let's find the corresponding values. So for x, let's pick -1, 0, and 1. We also include 0 because 0 is the y-intercept. Then the corresponding y values are gonna be 1/2 to the power of -1. That should be 1/2. That should be 2 to the power of -1. That should be 2, and the 0 is 1, and 1 is 1/2. And then for b, x values, let's go with -1, 0, and 1. Corresponding y values is gonna be 1/2 to the power of -1 is 2. It's gonna be 4. It's gonna be 4, 2, and 1. 4, 2, and 1. Yes. Okay, and then for number c, x -1, 0, and 1, the corresponding y values will be 2 multiplied by 3 is 6. Okay, and then 0 is 1 is 3, and then we have 1/2. It's gonna be 3/2. Okay, and then once we have those, we can sketch our functions. Let me draw the Cartesian plane. The Cartesian plane. Okay, these are your x-axis and these are your y-axis. It's important that when you are sketching, you always label your axis. I think there is marks for that in the exam. 1 and 2. 1 and 2, 1, 2, 3, 1, -2, -3, -1, -2, 1, 2, 1, 2, 3, 4, 5, 6. Okay, let's start with the first function of y is equal to 1 over 2 to the power of x, where x is -1, y is 2, and then we have 0 and 1, and then we have 1 and half. So that is your first function. And then let's sketch the second one. We have -1 and 4, -1 and 4, and then we have 0 and 2, and then we have 1 and 1. Hopefully you can already see that the function is stretched further away from the x-axis, and then lastly we have c. Then for c we have -1 and 6, gonna be here, and then we have 0 and 3, and then we have 1 and 1.5. 1 and 1.5. And 1.5, and that is how our function is gonna come out. So once again, by increasing the value of a, the function gets stretched far away from the x-axis, hence why it is called the vertical stretch. It is called the vertical stretch. As you can see that the red function is the furthest away, from the x-axis. It is more stretched away from the x-axis, hence why we call it we call changing the value of a vertically stretching the function, or hence why we call it a vertical stretch. Okay, next let's do example number 4. Okay, here what are we doing? Sketch the following functions on the same side of axis. Okay, we have function of a is equal to 2 to the power of x, and y is equal to -2 to the power of x. Okay, so now we are dealing with the negatives. So introducing a negative sign to the function, what does it do? You should be well aware or well familiar with what introducing a negative sign does to the function, and that is it flips or reflects the function about the x-axis. It flips or reflects the function about the x-axis. And also always remember to put brackets like I've done there when you are dealing with the negatives, because a -2 to the power of x, let me say, and b -2 to the power of x is not equal to -2 to the power of x, because when you are dealing with even numbers, you will have -2 multiplied by -2, which would give us a positive number. So always be careful to put the negative sign outside of the bracket, so that you can get correct values. Okay, now let's go ahead and sketch these functions. on the same set of axes, excuse me, on the same set of axes, okay. So you already know that with the functions a and b, those are the functions of the restriction b is greater than 1. You know, for those two functions, b is greater than 1, and then for this one is b is greater than 0, but b is less than 1. And we're basically dealing with the matter graphs here, okay. So let's quickly sketch these functions. Negative 1, 1, 2, 3, 4, 1, 2, 3, 4, negative 2, negative 3. In fact, let's just 1, 2, 1, 2, and I have 1, negative 1, negative 1, negative 2, 1, 2. These are your x and y values. Okay, so let's sketch these functions. For a, let's find the corresponding x values is negative 1, 0, and 1. The corresponding y values will be 1 over 2, 1, and 2, 1 and 2. And then for b, we're gonna have the x values of negative 1, 0, and 1. We're gonna have y being negative half, negative 1 over 2, and then we're gonna have 0. It's gonna be negative 1, and then 2 to the power of 1 is 2, is negative 2. Okay, and then for number c, I'll just write it here. The corresponding for c, x, negative 1, 0, and 1. C is 1 over 2 to the power of x, 1 over 2 to the power of x. So 1 over 2 to the power of negative 1 will be 2. And 1 over 2 to the power of 0 is 1. 1 over 2 to the power of is 1 over 2. And then lastly, we have number d. The x values we're going to use is negative 1, 0, and 1. And then corresponding y values for the d function. The d function, remember, it's y is equal to negative 1 over 2 to the power of x. Y is equal to negative 1 over 2 to the power of x. So 1 over 2 is negative 4. 1 over 2 to the power of x is 2. So therefore we're going to have a negative 2 to the power of 0 is 1. We're going to have a negative 1 and a negative half. Okay, let's sketch these functions. For a, we have negative 1 and half. It's here. Negative 1 and half. We have 0 and 1. And then we have 1 and 2. 1 and 2. 1 and 2. Of that nature. And next we have b. B is just the same function as a, but now the negative sign has been introduced. So we're expecting the function of b to be a reflection of the function of a. So let's go ahead and sketch this and see what happens. So we have negative 1 and negative half there, and 0 and negative 1 there, and 1 and negative 2 there. And then we simply join the dots. We simply join the dots, and you see that the function of b, the purple function, is just a reflection of the function of a. Okay, and then next let's sketch function number c. Function number c, we have -1 and 2. Here we have 0 and 1, and then we have 1 and half here, just like we did with the other ones. Join the function, we join the function, and then the other function of d, which should be the reflection of this function, let's sketch it. We have -1 and -2 here, and 0 and -1, and 1 and half, 1 and half. And that is how it comes up. These are curves, you know. So you can clearly see that this function of a, which is y is equal to 2 to the power of x, is just reflected about the x-axis in order to obtain this function of y is equal to -2 to the power of x. So always when a negative sign is introduced, you know, to a function, it will reflect that function about the x-axis. Let's come here once again to clarify that. So have a look at it. A negative sign will cause a reflection in the x-axis, so the function will be reflected about the x-axis always. Okay, next let's do the following example. Example number 5. Sketch the following functions on the same set of axes. So what happens here is that we now have a new asymptote. We have a new asymptote, which is 2. So that function has been shifted 2 units upwards. The function has been shifted 2 units upwards. But let's quickly sketch these two functions and see what happens, but remember the value of q now is 2, so y is equal to 2 is your horizontal asymptote. Now we have to show it on the x-axis. Okay, but let's quickly sketch the function x values -1, 0 and 1. Corresponding y values is gonna be 1/2, 1 and 2. Okay, and then for the b function x values, let's go with -1, 0 and 1. So the b function is essentially the same as the a function. It's just has been shifted 2 units upwards. So we're gonna have these corresponding y values. 1/2 plus 2 is gonna be 5/2 here, which is like 2.5, and then we're gonna have 3 here, and then we're gonna have 4 here. Okay, let's go ahead and sketch those now. Sketch those. These are your x-axis, y, 1, 2, 3, 4, 1, 2, 3, 1, 1, -1, 1, 1, 2, 3, 4, -1, -2, -3. Okay, so for number a, where x is -1, y is half, and 0 and 1, and 1 and 2, you join the functions, or you join the coordinates, the points. We join the points. Okay, and then let's draw function number b. Y is equal to 5/2. 5/2 is what? Is 2.5. 5/2 is 2.5. So is gonna be halfway there, and then 0 and 3, and then 1 and 4 there. Then we join our points there. So you see that these functions are actually the same. It's just that one has been shifted 2 units upwards. One has been shifted 2 units upwards. One has been shifted 2 units upwards in order to obtain the second function, so that is what changing the value of q there does to the function as the vertical stretching. It's also important to note that the second function has an asymptote at y is equal to 2. That is the horizontal asymptote of the second function. Horizontal asymptote of the vertical function. Okay, so I think that is straightforward. Let's go ahead and do example number 6. So for example number 6, we are given that function of y is equal to 2 times 1 over 4 to the exponent x minus 2. Okay, so yeah, it's quite something. We are asked to determine the intercepts of this graph with the x-axis. With the axis, so for number 1, let's get to answering it. We will determine the intercepts algebraically. So yeah, that is the function that we have there. Okay, for number 1, to determine for y-intercept, we let x equal to 0, and then we solve for y. So the y-intercept would be what? 1, y is equal to 2 times 1 over 4 to the power of 0 minus 2. 1 over 4 to the power of 0, that should be 1 times 2. Okay, the y-intercept will be 2 minus 2, that will be 0. And then for x-intercept, we let y equal to 0. For x-intercept, let y equal to 0. So our equation is equal to y is equal to 2 times 1 over 4 to the power of x minus 2. We let y equal to 0. This would be 2 times 1 over 4 to the power of x minus 2. We bring the 2 to the other side. 2 times 1 over 4 to the power of x. We divide by 2 on both sides. We'll be left with 1 is equal to 1 over 4 to the power of x. Remember laws of exponent, so y over 1 over 4 to the power of 0 is the same as 1 over 4 to the power of x. Therefore, x is equal to 0. So yeah, the x and the y-intercepts are actually 0. Those are the intercepts. That is where our function would cut the x and the y-axis at the origin. Write down the equation of the asymptote. So for number 2, equation of this asymptote, I've always told you that for the equation of the asymptote, you just read it from the equation itself. So it's y is equal to negative 2. Y is equal to negative 2. Y is equal to negative 2. And then for number 3, we have to sketch the function. For number 3, we have to sketch the function. Okay. So in order to sketch the function, let's just find another point. So we already know that the value of p is between 0 and 1. So our function will be of this nature. So let's just find some few values let's go for -1, where x is -1, where x is -1. Let's find the corresponding y value. Should have said let x equal to -1. What is our formula? Is 2 multiplied by 1/4 to the power of x minus 2. We just need one other value, because we already have we already have the asymptotes and the x-intercepts. So I'll just only calculate one other value, and then we'd get to sketching our graph. 1/4 to the power of 2 multiplied by 1/4 to the power of -1 minus 2, and that is 6. That is 6. Y is equal to 6. Okay, now let's get to sketching. This are the x-axis, these are y-axis. Okay, we know that the function will cut the x and the y-axis. Oh, okay, I forgot to calibrate the x and the y-axis. 1 2 3 4. So use 2 4 6 8 -2 -4 1 2 3 -1 -2 -3. Okay, so what is the asymptote? The asymptote is -2. So let's draw the line of the asymptote. Our graph will not go below this line of y is equal to 2. That's the horizontal asymptote. Okay, and then next, that other point that we calculated, where x is equal to -1, y is equal to, we have the point there, the intercept, and they have -1 and 6. We have -1 and 6. Then once you have that, you simply join your points and make your curve. And that is our function. That is 2. Okay, that is how our function will come out. Okay, and then for number 4, we also explain the transformation from y is equal to 1/4 to the power of x to y is equal to 2 multiplied by 1/4 to the power of x minus 2. Okay, so you can see there that we have the value of a, which stretches the function, and then the function has been shifted to in its downwards. Okay, so for number 4, the transformations that were made to the function of y is equal to 1/4 to the power of x function was stretched by a factor of 2, and to find y is equal to 2 multiplied by 1/4 to the power of x, and the second transformation, and then shifted 2 units down to get y is equal to 2 times 1 over 4 to the power of x minus 2. So those are the two transformations that have been made to the function. It has been stretched by a factor of 2, and then it was also shifted down by 2 units. Okay, so that is that with today's lesson on exponential functions, which is the last part of the functions. So on the next lesson we're gonna be going into further characteristics of the function. So we'll be looking at your domain and range, looking at the domain and range, and also finding the equations of the function if you are given a graph, so kind of working backwards, and then we will start doing past papers. Until we meet again, I wish you good luck and good studying.